Welcome to the Explainer. Today, we're diving into the ultimate locked room mystery. What's actually beneath our feet? I mean, think about it. If you could somehow dig straight down through your floor, through the soil, past the bedrock, and just keep going, what exactly would you find? Let's start with the massive curiosity gap. We actually know, in remarkable detail, exactly what's happening thousands of kilometers down. Yet, and here's the crazy part, no human, no machine, literally nothing has ever actually seen it. For most of human history, the interior of our planet was just a massive blank space on the map. To give you some perspective on our physical limitations here, the deepest hole humanity has ever dug is the Kola super deep borehole in Russia. It reached about 12 kilometers down. Now, 12 kilometers sounds like a lot, right? But to get to the center of the Earth, you have to travel 6,371 kilometers. So that massive, record-breaking drill hole, it barely even scratched the outermost skin of the planet. Section 1. Earth's layered onion. Okay, let's look at the physical structure. We've learned that the Earth isn't just a solid, uniform ball of rock all the way through. It's actually structured in layers, kind of like an onion, or maybe a hard-boiled egg. Peeling back that first layer, we find the crust. This is the rocky outermost shell, the very skin of the planet that we live on. But even this super thin layer isn't the same everywhere. It actually ranges from a mere 5 kilometers thick under the deep oceans, all the way up to 70 kilometers thick under those massive mountain ranges on the continents. And this setup brilliantly illustrates why our world looks the way it does. There are two main types of crust. Oceanic crust is mostly dark, dense basalt. Continental crust, on the other hand, is much thicker, but it's made of less dense granite. It's like, well, think of a lighter block of wood floating higher in a bathtub than a dense piece of metal. In exactly the same way, our less dense continents literally float higher on the Earth's interior than the dense ocean floors do. Right beneath that crust lies the mantle. Now, this is the heavy hitter of Earth's layers. It's a staggeringly thick zone, nearly 2,900 kilometers of hot silicate rock. To put that into perspective, it makes up a whopping 67% of the Earth's entire mass. And while it is mostly solid rock, it behaves in a really unexpected way over long periods. What's totally fascinating here is this concept of plasticity over time. The rock down there is so incredibly hot, reaching over 3,700 degrees Celsius near the base, that it actually acts a lot like silly putty. You know how if you hit silly putty with a hammer, it shatters like a solid, but if you just leave it sitting on a table, it slowly oozes and flows like a really thick liquid? Well, the solid rock of the mantle does exactly that, flowing at a crawling pace of just a few centimeters every single year. Plunging even deeper, we finally hit the core, which starts about 2,900 kilometers down. This is a massive metallic center made mostly of iron and nickel, and it's actually divided into two distinct parts. First up is the outer core, which is pure liquid metal boiling away between 4,400 and 6,100 degrees Celsius. Because it's liquid, it's actively flowing, and the constant churning of this electrically conducting metal, that is exactly what generates the Earth's magnetic field. But wait, at the very center, the inner core, we run into a bit of a paradox. Temperatures down there can easily top 5,000 degrees Celsius. Guys, that's roughly the temperature of the blazing surface of the sun, which naturally makes you wonder, how on earth can a ball of iron and nickel be that insanely hot and not just instantly melt into a liquid? Well, the crucial factor here is pressure. The staggering, frankly unimaginable weight of all the rock and metal of the entire planet pressing down from above compresses the inner core so intensely that the iron atoms are literally locked tightly in place. They simply don't have the physical room to move or flow, so the inner core remains entirely solid, despite the mind-bending heat. Section 2. The Seismic Detectives. Now let's pivot from the what to the how. Because if we can only drill 12 kilometers down, how do scientists know with absolute certainty that the core starts exactly 2,900 kilometers beneath us? Well, the key wasn't a bigger shovel or a massive drill. It was waves. When an earthquake happens, it acts kind of like a giant, energetic flashlight. It sends vibrations, seismic waves, radiating outward in all directions right through the Earth. It's exactly like ripples spreading across a pond when you toss a stone in. Scientists basically rely on two main types of these waves. First, you've got P waves, or primary waves. These are fast. They push and pull material in the exact same direction they're traveling, sort of like a stretched out slinky. And crucially, P waves can travel through solids, liquids, or gases. Then you have S waves, or secondary waves. These are a bit slower, and they shake materials side to side, more like a flicked rope. And here, right here, is the absolute key to our whole mystery. S waves cannot travel through liquids. Since a liquid has no real rigidity, the very second an S wave hits a liquid layer, it just completely stops dead in its tracks. Section 3, shadow zones reveal all. So, whenever a massive earthquake strikes, seismometers all over the globe start recording the waves. But here's the thing, they don't arrive everywhere. Because S waves absolutely cannot pass through liquid, they travel fine through the solid mantle, but the second they hit the boundary of the outer core, boom, stopped dead. This actually casts a massive shadow zone on the exact opposite side of the planet, starting at about 104 degrees away from the quake, where no S waves are ever detected. And this vast shadow, it's the single strongest piece of scientific evidence we have proving that the outer core is, in fact, a liquid. Now, P waves, if you remember, can survive going through that liquid outer core, but they don't just travel in a perfectly straight line either. When these incredibly fast waves pass from the solid mantle into the much denser liquid outer core, they bend or refract. This bending drastically redirects the waves, which ends up leaving a distinct ring-shaped shadow zone between 104 and 140 degrees where no direct P waves are recorded at all. Section 4, Lehman's core discovery. But this story of mapping the inside of the Earth takes an amazing turn in the early 20th century. Enter Danish seismologist Inge Lehmann. Back in 1929, she was poring over seismic records from a really powerful earthquake in New Zealand, and she noticed something that seemed literally impossible. Incredibly faint P waves were somehow sneaking into that ring-shaped shadow zone, the exact place where absolutely no P waves should be. So Lehmann proposed a brilliantly bold explanation. In a groundbreaking 1936 paper, she mathematically proved that these rogue waves were actually refracting and bouncing off an undiscovered, totally solid inner core, hidden deep within the liquid one. And sure enough, improved global instruments quickly proved she hit the nail right on the head. Section 5, the supporting clues. Now, seismic waves are a brilliant tool for sure, but any good detective knows you need corroborating evidence to fully close a case, right? We can't just rely on earthquake echoes. And man, the supporting clues here are absolutely fascinating. First off, iron meteorites, which are basically fragments of ancient asteroids, match the exact iron-nickel compositions scientists predict for our core. Second, think about density. The Earth's surface rock density is about 3.0 grams per cubic centimeter, but the planet's overall average density is 5.5. That means there simply has to be something incredibly heavy and dense hiding in the middle to bump that average up. Add in the fact that our global magnetic field strictly requires a liquid metal dynamo to exist, plus physics calculations of the Earth's spin, its moment of inertia, which prove the heaviest mass is dead center at the core. All of these entirely independent clues perfectly lock together like a giant puzzle to confirm this layered metallic core model we've been exploring. As we wrap up this explainer, I want you to do something. Just look down at the floor beneath you one more time. We now know it is absolutely not just an endless, boring expanse of static rock down there. It's a dynamic, layered heat engine. The intense heat from that deeply buried iron core is constantly flowing outward, driving the slow, churning flow of the mantle above it. And that flowing mantle, well, it literally moves our tectonic plates, constantly building up and destroying the very ground we live on. So the next time you feel the ground shake, or you look up at a massive mountain range, ask yourself, what other incredible secrets is that dynamic heat engine beneath our feet still waiting to reveal?